Okay, all right. So, everyone, welcome you all once again in week 7 for the course of Introduction to Machine Learning instructed by Professor Balaraman sir from IIT Madras. Okay, so in this week we are going to see yes, audio is audible. Okay. So in this week, we will see the evaluation measures, cross validation, ROC curve, and ensemble method. So basically, we started with simple introduction of supervised, unsupervised, and reinforcement learning, and we have started supervised type of mechanism, right? So in supervised, there are two tasks: classification and regression, and up to week 6, we spend the 5 lectures especially for this supervised study for regression and classification. So we have seen multiple variants of regression. We have seen multiple algorithms related to classification, including neural network, support vector machine, discriminant analysis. Last time we have seen decision trees also. Okay, so now I think you now have an idea that what is supervised study, how machine learning supervised algorithms works. Okay, whether it's a case of classification or regression. So now we will see how to evaluate, because whenever I say you, if you are developing any algorithm, especially in supervised study, we will see some evaluation in unsupervised also, but let's stick to supervised study here. So for supervised study, you have created a model and your model is giving you some answers, the predictions. So we created some loss functions for that, right? If you remember, we have some mean square errors, or we have maximum likelihood type of loss functions, which helps you to optimize your algorithms. Okay, so those are loss functions. Now after using those loss functions, having all the optimization, final model is in your hand, and now that model is so much refined that if you give some input, it will predict you some output, and according to you, because you have optimized it, the output should be good enough. But question arises, okay, now your model is developed, how can you say the output is good enough? So here comes some evaluation measures or performance matrices, we can say. So what are these performance matrices, how we will evaluate it, we will see today. Secondly, there are high chances of overfitting. Generally, we don't have a problem of underfitting, because if your model is underfitting, it is majorly related in two cases. First is either your data is very small, you have a very biased type of data, and that's why your model is underfit. Otherwise, your model is too simple, so that's why it is underfitting. For example, you have a huge amount of data and you are using just two-layer perceptron there, so obviously it will not give you a good answers or good predictions. So in general, we don't have a problem of underfitting, we generally have a problem of overfitting. So how to see if overfitting is there, how to remove that, what are the different measures, or what are the precautionary things that we can do to handle the future overfitting in the model. So we will see that. So this cross validations is related to that perspective. Third is this ROC curve is related to evaluation measures, and one type of method, this is ensemble method, is there for some another thing that we will going to discuss. Okay, so evaluation and evaluation measures. So as I told you, you have a model, you have this model, now you have to check whether it is good or bad. It means that this model is the one which is optimized. Okay, so don't confuse with loss function and these performance or evaluation measures, because loss function are the functions which helps to optimize your model, but evaluation measures are basically just to evaluate you. So let me give you one example. So let's say you are studying here, so you individual as an individual is a model. When you are coming here in the first class, and I am taking you a test, right? So the output of the test is your evaluation measure, is your evaluation criteria. Using that, you are optimizing yourself. So if same criteria is used to optimize, then we can say that evaluation and loss are same. Otherwise it can be different also. Okay, so where it can be different we will also see, and where it can be same we will discuss that also. So basically evaluation measures and or evaluations are the measures that how well a model is performing on a given data, or it ensures that model generalize well beyond the training data. So it means that if you're coming to the class, we are giving you some input in the form of ppts or some lectures, and we are testing you at the testing time. So in class and in the test class the questions will be different, right? So that's why we wanted to ensure that you have learned the concept rather than you are cramming the particular concept, right? So here also these evaluation measures um, are especially used to ensure that your model is generalizing well. Okay, so how to ensure that, we will see how to process this thing. We will see what are the steps that after your model uh, development, how to use these measures, we will see in the upcoming slides. So common classification evaluation measures, generally we are starting with this classification. So for classification type of task there are multiple evaluation measures. So first is misclassification. It means it's a 0-1 loss. So it's a, yes, any doubt? So misclassification error, it's a 0-1 loss, we can say. Why we are saying a loss? Because generally the losses are related to the error terms. Okay, wherever you find this term error, uh, we can replace it with loss as well. But generally in machine learning or deep learning, we use this term loss, which is especially going to help for the optimization. Okay, so as a optimization function if you are using it, then you can say it as a loss. So first criteria is misclassification error. It means fractions of incorrect prediction. So let's say you have 100 samples of class A and B. Okay, so and I want to predict that how many samples are incorrectly classified. So number of samples A correctly classified is, let's say, 30. Number of samples B correctly classified is as say 50. So it means total number of correct samples are 80. So misclassified samples are 20 by 100. So it will be 0.2. Or in the other sense, in the opposite sense, we can say 0.8 is the correct classified. So 0.8 is accuracy and 0.2 is misclassification error. So either you are working in terms of accuracy, or you are working in terms of misclassification error, it doesn't matter. So if you are talking about error, then obviously the less is better. If you are talking about accuracy, it means the more is better. So whenever you are defining these evaluation criteria, wherever you will find this in a table, let's say accuracy is written. Okay, so you will find this arrow. It means that the higher the better. If you will see some any MSc loss or something, you will find this error downwards. It means the lower the better. So if you are going to compare two models with misclassification error, so the lower misclassification error model is better one. In the opposite case, more accuracy is the better model. Okay, so these are the two evaluation measures, simple evaluation. In between it is written as cross entropy loss. So it measures how different the predicted probabilities are from the actual labels. So it means that this cross entropy loss is generally treated as loss function. So for the performance we do not treat as for the evaluation, we treat it as the evaluation in terms of losses. So whenever you are going to optimize it, the main optimization function used there is as cross entropy loss. So cross entropy loss works on the formulation that how much your predicted probabilities are far from the actual labels. So ultimately, if you remember, I told you in neural network, if the final layer is of regression type, then the neuron can give the final outcome as a number, no worries. But if your problem is formulated for a classification type, then the outputted number is treated as a probabilistic function. So a probability is written out of it. So for example, let's say I have a two classes A and B. A and B means 0 and 1, I am saying. Okay, 0 and 1. And I am saying the outcome predicted from the neural network is 0.95. So it means 0.95 is the probability for class 1. So it means that this is the probability associated with class 1. So it's a high chances, right? But it should give as 100%. So it is somehow far off about 0.05. Okay, so this is how you measure this cross entropy loss, and it is generally used for loss functions rather than the final evaluation measures. So similarly, as we have discussed with classification, there are multiple regression evaluation measures. So first is mean square error. It means, let's say you have an output that is the true value and you have a predicted value. What you will do, take the error, take its square and take the mean. So this is mean square error. Simple, what we have learned in the last lectures as well. Second is root mean square error. Why the root is coming here? Because we are taking it in a square terms. So this someone say ki if you are taking a square of something to neglect its effect and to convert the error in the original units, take the square root. So root mean square error is simply the root of the mean squared error. Okay. Third is mean absolute error. So generally we put this square to neglect the effect of positive or negative signs. So someone says ki why only take the squares? Let's take the absolute value. So it is mean absolute error. So basically, if you are using mean square error, it means it is penalizing larger errors more. So let us say ki you have a task of age prediction, okay, and your model is giving wrong answers for the ages, let's say for 60, 70, these type of ages. If the age is less, the your model is quite good. So you can use their mean square error because it will penalize larger errors more. So if the error is large, it means it penalize more. It is giving more attention towards the samples which is causing more errors. Okay, so sometimes it is helpful, sometimes it is not. It depends on the model and the data that is under your training, right? So for that, to neglify this thing, we can use mean absolute error where it is giving the equal weightage to all. It's more like that. So there are multiple other evaluation measures as well, but these are very traditional type. So another can be some the hybrid form or derived from these measures. So that's why we have included those traditional methods that helps you to evaluate your models. Okay, so for classification, generally we use accuracy or cross entropy loss, and for regression we generally use for mean square error, root mean square error, and mean absolute error. Okay, so now evaluating the classifier performance. So we have discussed about multiple evaluation measures. Now we start with how to evaluate some classifiers or models performance. So our goal is to measure the performance on the entire data distribution. It means that we have some data D. Okay, let's say if we have 1 lakh samples or 1 million samples, so all from on all this data we wanted to measure the performance on a particular classifier. Okay, plus why we are taking the entire data distribution, why we are talking about it, because theoretically we are modeling on the basis of data that is given to us, but ideally we wanted to match the exact distribution, we wanted to learn the exact distribution underlying the data. Sometimes data is so much representative of the true distribution that your model is so good. Sometimes you are biased or the variance is high in the data. In those forms, the it cannot represent the true distribution. Okay, so when we don't know the full distribution, we only have samples ultimately. So samples can be good, samples can be bad. So using the training and test data to estimate true performance, so what we do is generally you find here two terms, training and testing data. So first we divide the whole data into two parts. First is training and second is testing. So what we are going to do, we use the training data to update weights. weights, or you can say parameters. So using this data, we are updating the weights, we are updating the parameters, and when you update the parameter, you just check the model on test data. So it means that when you are coming to class, what I am teaching you or what the other supervisors teaches you, is this data is completely different, or somehow some of the data is different what is given you on the testing time, right? So just think about it. If we merge the data, if we tell you the question in advance, then how can you say that your learning is well? So that's why we keep these two types of data separate, and we disclose, yeah, we on your mark sheets we only give the evaluations on the basis of your test data, right? In the classes, if let's say ki after this class let's have a quiz, a simple quiz, I'm not taking those quizzes into account on your mark sheets at the last. So those questions or those examinations will be you will be included in your mark sheets, which are completely for the testing data. Okay. Someone has opened the mic. Any question? Okay. So that's why first thing is we have to split the data into two parts, that is train and test. So training set is used for learning model parameters as I just told you, and test set is used for final evaluation. So generally when you see some papers or something, they used to have a training and testing evaluation separately. It means that this is the training error, this is the testing error, or this is the training accuracy, and this is the testing accuracy. So let's say some student is performing so well in the regular classes. Let's say that student is getting 95 percentage in regular classes. It means on the training data, I teach you something, I ask you something related to that, you are good. But as the testing come on the final exam, the accuracy dropped to 65%. Okay. So for a model on the mathematical view, we can say that if the accuracy is much higher on the training side and much lower on the testing side, it means this is a problem of overfitting. Okay, so what we wanted, we generally want these two accuracies nearby to each other. It can be possible that it is 95 and it is 93, or it can be 96 also. Okay, it is valid, no problem. Sometimes some changes are there in the testing data, so it can happen that accuracy might increase, might decrease, it can happen. But it should not be like this much difference, or 95% or 65%. It means your training is not well. Okay. So so what can be the issues related to this? So the test data may not be independent of training data. It means that there are the same samples in the testing which are taken from the training. So if you are using that, obviously you are creating a bad testing set. So you should not do that. And training data may be biased, not representative of the real world distribution. So these two things we have just discussed. First thing, that this is the first step before any model or something, that use the data which you can say that it's a representation of the true model. For example, if you are classifying, you have a task to classify um, um, or you can say you have a task to identify a face. Okay, face identification. So generally this face identification, you cannot have the data from all over the world, right? So that's why face identification is dependent on the organization. Okay, so because this organization have a limited number of people, they can include all of them at one place, right? If the task is to just to predict that what is the age of the person, now this age of the person is not dependent on any organization, so for that you require a lot of training data. Or let's say you in your data, the samples are more of a young age, right, people. So you don't have much data for older age, you don't have much data for younger age. So it means that your training data is not good, your data is not good actually. So you have to think about that what can be the testing scenario. If in the testing scenario your data is meeting well, then obviously the data can be, we can say that it's a representative of the true distribution. Otherwise we have to think of how to collect more data. Secondly, this second issue is the testing. When you are splitting the data of training and testing, you should be ensuring that testing should also represent the true distribution, and it should be different from the training set, because the most challenging examples if you are putting in the testing set, then you can say that your model is quite well. Okay, so let's say if I give you an example, if I give you a very hard test, okay, in which some brainstorming questions are there or something, and some student is passed with flying colors, so it means that that student has learned the concept so well that he is able to question these hard or challenging questions. If I give you a mediocre type of test, then okay, I can say that the student is also good, because he is able to achieve or maintain the accuracy which he is achieving in the training classes as well. But if my testing set is completely biased or took from the training data itself, then I can't say that the student is generalizing well or something, right? So we have to make sure how you are splitting these training and testing sets. Okay, so first is, if you are going to create a model, you will have some data, divide it into two parts, training and testing. Okay, for testing for evaluation, training to update weights. So to divide these two things, two sets, you have to make sure that these two will be a good sample sets. Okay, ऐसा ना हो कि they are biased or they are not represented of the true distribution. Okay, so first thing is you have to divide it. When you divide these set, use the training set to train the your model, and after training use the testing set to evaluate your model. So this evaluation is given as a performance metric. Okay, your model is now 95 or 96% accurate. This is how we do generally the pipeline. Now question arises, let's say if there are 100 samples. Okay, generally what we do is we put a ratio of testing and training. So if I am saying it's a ratio of 70/30, it means that this is used for training and this is used for testing. Obviously you have more data in training and less data in testing. It is a journal rule. It's more like an intuitive thing. But today there is a study of few shot learning. Okay, so few shot learning, it, as the name suggests, here the training data will be very low and testing data will be very high. It means that if you are saying one shot, it means that only one training sample is given and rest of the samples can be treated as testing. The model is able to learn at the runtime in the dynamic. Okay, zero shot means you don't have to give anything to the model. The model is so much well already established. You just give the sample and the model will be able to give you the predictions. So basically there are also studies going on like that. But in traditional machine learning, in traditional train test split, we generally keep more amount of data in training and less amount of data in testing. So minimum ratio can be 50/50. Okay, for this type of thing we generally keep it as 70/30 or 80/20. This is the ideal splits, these two, 70/30 and 80/20. So if you are having less amount of samples, you can go for 80/20 as you need more data for training. And if you have sufficiently good amount of samples, you can go for 70/30 or 60/40. It's okay. So first of all, you decide this ratio. Okay, so let's say I decide this ratio as 70/30. So out of these 100 samples, 70 will be treated in as training, 30 will be treated as testing. Okay, no problem. It's a simple thing. We can randomly divide these splits. Now, do you think this single train test split is able to determine good results? It means that I have one big basket, and because I have to think about the training and testing should be so much accurate, it should not be biased, it should not be like testing data should not be very different or very close to the training data. So we don't do anything regarding this thing, thinking about too much and putting these things explicitly. What we do is we randomly divide 70/30. Okay, and go for the training testing what we are going to do. But someone says it can be possible that if you choose some another samples for training, your testing accuracies will be different. It can be possible. Yes or no? Right? So for that, a term comes into picture, that is cross validation. So what they say that when you are splitting the data, you should not split it only one time. Just we just have a method that we can at least split k times. How much k? For example, let's say I am saying the data is maybe divided into, let's say my data distribution is 75 ratio 25. It's for you to easily to understand. Okay. So it means that let's say this is your data. So 25%, this is the 25%, this is testing. Okay. Rest of the data is training. So I also divided into, so I have divided data into 4 equal parts. So one portion is keep for testing and another portion is for training. It's good. It's a first split. Now someone says you have chosen this split as testing, another as training. What if you have changed this split testing to this portion, not this? Will the accuracy change? Yes or no? So these are the question comes in the mind that whenever we are using this random thing. Okay, so they say that okay, don't worry, we have our model ready, we have full training strategy ready, let's do this thing. So what we are going to do, first we divide that full data set into equal parts. Okay, so here I have divided into 4 equal parts. I have kept first portion as testing and remaining as training. So this is my first split. Now I will change my testing split. Second may the same these same partitions, from the same partitions I keep the second portion for testing and another as training. So this is my second split. Similarly, in third split I take this one as testing, in the fourth split I will take this one as testing. So what I am doing, I am keeping one split as testing at each time. So this, what is this doing, it is removing the this randomness. Okay, so what we can do, after these 4 splits we can take an average. So now we are not like this specific testing split is used for testing, that's why your accuracy is so much low. Maybe some another testing split can have a good accuracy. So to remove these redundancies or remove these ambiguities, we use this type of train test split. So this type of train test split is called as cross validation. So what we are doing, we are validating it multiple times. So we are taking first split as a testing, second split as a testing, third split, fourth split. So if you are dividing your data into k splits, obviously, okay, so these are the k splits, or we can say that train or k on k minus 1 subset, test on the remaining subset, so that remaining will be changing every time. Okay, so this is how this strategy works, and we call it as cross validation. It generally we don't apply it if we have a very large amount of data, but if you have small amount of data and you have good computation power as well, we generally go for these strategies. Okay, so what we do, we iterate this train test full method for each every validation scheme, and at the end we take an average. So while reporting the results also, we say that we are applying this k fold cross validation. K means, let's say you have here it is 4 fold, because we have 4 folds here, first, second, third and fourth. So if you have 10 folds, you can keep it as 10 fold cross validation. So as you increase the number of folds, obviously the computation takes more time, and complexity will be high. Okay, so this is called cross validation. So as you can see from here also, so the testing set is, the portion of testing set is fixed, and every time a new subset is taken, and these subsets are mutually exclusive. Okay, so if you can see from the figure, the samples that are used as testing in this fold will not be used in any other fold. Okay, so it means that the testing set is mutually exclusive at each folds. Okay, so any question related to cross validation? Is it clear, cross validation thing?
Ma'am, I didn't get the last bit of it. I understand that you're testing. You've divided into K folds, and you're testing one
Hmm.
uh, and training with the other. But let's say after all that, all you're doing is averaging the result, like the average part.
Yes, yes, yes. For example, let's say, if I give you an example, let's say I have four folds: A, B, C, and D. So here my testing one is A. Okay, let's say my accuracy is 90% here. This is my first fold. Second fold, my testing is B. So let's say I get the accuracy of about 60% here. It can happen that B is so much challenging that it is not able to give you a good predictions. For the third fold, I have C. Okay, so let's say I have an accuracy of 85%. And for fourth D, let's say I have an accuracy of around 95%. So what I will report, I will say I have created four folds and the final accuracies are 90, 60, 85 and 95 respectively. So the on average, the complete testing accuracy of this model is the average of all this. Getting my point?
So that is the accuracy that you're saying.
Yes, yes, yes.
That
This
is
is
average.
this is accuracy. This is accuracy. Yes. So
But then how does it help us with the end weights? At first I thought, is it the weight that we are averaging out?
no, no, no. Now I'm not talking about weights here. I'm not talking about training here. In today's class is not for training. No training. I'm not talking about training. The data that you are training BCD, let's say this the model is training on this data. The weights updation, everything we have learned in the last classes. That is fixed. I'm not changing that. Okay. After applying all optimization, after getting the final model on this BCD training, use the same model just to test on A. You have not used A for training. For the weight updation, you have not used any sample that is present in A. You are just going to use it for testing. I have created the model. So it means that this BCD is the data that is given you in the class. Some questions, practice questions is given in your class. This A means your final exam set. There you have not gone through any questions that is in the classroom के कोई questions नहीं है. Now you are putting your brain, giving the answers. You are giving me the answers like 90%. Okay, good. Sometimes you also say that na, today my day is not good, the exam is too difficult for me, according to the training, so that's why I didn't perform well. It can happen, right? So let's say I reiterate this process with the different data set. Now for the second fold, I have A, C and D for training. So on A, C and D training, let's test on B. So there it is 60% accuracy. So I am choosing some test set out of your data, and that can be random. Getting my point?
Okay, so this is only about rating the model. That's it. It's
Yes,
does
yes,
nothing to do
yes.
with training. Okay.
Yes, yes, yes. Yes, you can say that. Why we are focused here? Because look, means if I can put it in this way, um, you as a student, okay, have some mechanism to learn, right? I'm not sure that whether you are learning good, not good. Maybe you are giving me too much good answers in the class, you are getting good marks in your examination, but sometimes in the real life when you will go out for an interview of a company like a Google, you're not able to solve questions. Okay, I'm not saying you failed. I'm just saying your training data maybe has some bias that you are not able to solve question at Google. It's okay, it's completely fine, right? So as a human, I am not just saying be demotivated, blame yourself that you have not learned well. No, you just have to plan a strategy that okay, I have not been prepared for these much examination, I need to train more. Okay, so is this observation you get after you have some evaluation on some testing set. All right, so this is also important in machine learning perspective. Whenever you are training your model, it's all about parameters, right? Whether you talk about SVM where you are learning some boundaries, whether you are talking about neural network which is highly black box type structure, So those weights are training, those parameters are training with some values. You don't know anything about that. At the final end, if your model is giving you good results, it means it is good. But you have to make a model which is so much generalized so that it can be used in the real world. Ultimate main goal of any computer scientist at this era is like it can be used somehow in the real world, whether in the form of application, whether in the form of web application. And generally we are using phones right now, so we need any android or some mobile app for that, right? So how can you say that your app or your model will be so good when you will be testing it on challenging samples? So more the challenging samples you are passing, you are saying that your model is so much accurate. So that's why this evaluation is very much of concern. And secondly, why it is also concerning that most of the people who are going to use your model do not have any information, any knowledge regarding your this machine learning. They know these terms only. Ki, yeah, AI is here today, these chat GPT is here. What is GPT? If you ask your parents or your any of the worker around you, they will not know that. They say the chat GPT, are wo hai na, where you ask question, it will give you the AI answers. Okay, so they don't know anything about that. They only know these validations, these evaluations. So for example, if I tell you one experience of mine, we are working in agriculture field basically. So whenever we talk about agriculture, whether to farmers or Indian government, they don't know. Even they know about what is AI, they ask us only one thing: whether your model is so good that it can classify any of the crop present in the world. So we have to make sure them. So if we are saying ki, okay, our model is, sir, 80% accurate to classify this is crop, this is a apple tree or not. So what they will say, okay, let me give some, let's take your camera, take your application in an orchard in Kashmir and or Shimla, let's click a photograph and let's see that whether your model is capable to classify it as a apple or not, right? So they know these things very well. So this accuracy, this error, they know it, they can understand it. They will just say you, no, your model is good, yes, your model is good, on the basis of the testing set that they are having. Because we don't know what will come in the future for this app. So we wanted to create, yeah, we wanted to collect that type of samples, that okay, we should have these samples in the testing set, that our model is able to learn, model is able to classify. So that's why these performance measures are very important. Ultimately, at your perspective, if I say, when I was also at this stage, whether when I don't know about these models, and so our main goal is for the training part. We thought about, we always think about which strategy can solve this problem, how the network should be looking like, what optimization should I apply. So this is the more part of a technical side, which for which you are there, okay. But you are a mechanic, or you are a person who knows about electricity, but you are working for the people who don't know about them, right? So whenever an electrician comes to your house, he knows ki which wire is where to put or so. Ultimately you say ki, okay, this fan is not working, or it is creating too much noise, I don't know what you are doing inside. But the ultimate thing, oh, that electrician is so good, he makes our fan in just 3 or 4 seconds. Every fan he is able to do that. So this is how we are judging for from the user perspectives, and their perspectives are the ultimate thing. Ultimate goal is to serve the people, right? So these evaluation and performances are generally on the user perspectives, these are not from the developer sides. But because we are smart people, right, we can't say that ki work hard, ये तो वही वाली बात हो गई कि let's make food, and after making the food, serve it to the customers, they will say कि oh, ये वाली चीज गलत है, आप इसको ठीक कर लो. No, we can't do that, okay. We have to be very smart. So what we think, we go for the reverse engineering. So we think about कि okay, people can have these challenges in their data set, why not we include those things traditionally when we are training. So we think about those scenarios which can present in our future, right? So whenever you are preparing for your examination, you also do that. You say कि, okay, we have been we have gone through a lecture of neural network, there is a question of back propagation, and ma'am only let us know about this sigmoid function. Let's try for 10h function, because it can also come, right? So it's not like that you are not able to solve, but if we are predefinedly thinking about that, so you will be preparing for that also. So in this similar way, as a data scientist, we think of those scenarios, we think of those situations that can cause problem. So to remove those problems, we finally strategize our techniques or algorithms for that situations as well. But ultimately today we are specifically discussing about testing side, we are not talking about the training side. But yes, these are the precautions that we can make. So these precautions or these observations are just because from the testing. I'm not saying I'm doing anything new in the training, but from these observation, okay, I have to be very careful about it. Who can think of ki let's the testing and training data should be separated? Someone has like in whenever your model is going to be deployed, you will have much more real conditions, much more like that. So some of the studies uh, at present, whenever you find any good research papers, what they do is, because we can't find good data, right? It's a problem today that we can't find good real data, and we can't train real data on our systems, because we need huge amount. So what we are doing using this generative AI, we are generating synthetic data, artificial data. We are training our models, and we are deploying in the real fields. So, and just testing out that whether our models which are trained on synthetic data are capable to handle the real world situation or not. So this is how we are progressing in this domain where the data is the most important tool. Okay, so if there any doubt, then you can go ahead.
No, ma'am, I understood. The entire thing is about testing.
Right. Okay. So this is one of the strategy that this, because just think about, this is all a connected thing. I am talking about testing. It's okay. You say, ma'am, testing is so much easy. Keep one portion. Now question arises, why to keep only one portion? So that's why here come this strategy of cross validation. So okay, don't keep one portion. Test on every portion. Right. Next is overfitting and generalization. So as I told you, when we are optimizing our model or training our model, we don't have any indication that whether your model is overfitting. How can you say that? Means if you are in the training phase, how can you say that your model is overfitting? Because the overfitting nature, if I say, it's more like training accuracy is so much higher and testing accuracy is so much lower. It means like it's more like 95-65. Okay, so during training you work in iterations, right? Let's say on iteration 1 the accuracy of training is 60%. On iteration 2 it increased to 65. On iteration 3 it increased to 68. I am giving you random values, okay? Don't go for that ki ma'am is this much jump is shown or not. Okay, let's say fourth it reaches 90, fifth it reaches 95, sixth it reaches 99. Okay, so it is increasing, no worries, it is not decreasing. So you will say ki my model is again and again optimizing. But there is another problem, that this increasing training accuracy can lead to overfitting. Okay, so it's more like ki I am giving, means your model is specifically sticking itself to the given samples only. It is not generalizing things, it is just making out some analysis or patterns that is present specifically for the samples. So overfitting is model perform well on training data but poorly on unseen data. How to remove them? So to remove this overfitting, we use regularization steps. Okay, so these are the steps that we already include in our systems. So first thing is L1 L2 regularization that we have discussed in regression class, where we have learnt about L1 that is called in which your samples are added, some bias is added to the main optimization function, so that it restricts the values over your weights. आपकी weights पर restriction लगाता है, right? So your weights cannot be too high or too low. It's more like that. So these are called L1, L2 regularization, which are included during mathematical formulation. Okay. Another is data augmentation. So data augmentation I will talk about after making this point of dropout. Okay, data augmentation I'll tell you right now. Third is this dropout. This dropout we have learned in neural network, when we have learned neural network, where the all fully connected weights, among them some are dropped on the basis that they are not included or they are not very effective in learning. So it's more like dropout. Now I will talk about data augmentation. Okay, so let me ask you one question. So my question is, wait, is there any space I can write?
Ma'am,
Hmm, go ahead.
ma'am, in real, when handling real data,
Hmm.
how will you know that your model is overfitting?
Generally overfitting comes with two things, that whether your training and testing, how training and testings are you know uh, are in effect. For example, your model during training is giving you very good results. Okay, let's say medical data. So for a medical data, I have want to create a model which diagnose a particular type of disease. Okay, so the disease can be simple, like or fever related diseases. Okay, आपके typhoid, this TB or malaria or something. So those have simple some of the symptoms that are different from each other, but otherwise majorly related to fever and cough. Okay, so let's say you have a data of some patients. So how you collect data? You generally collect data from real world. You go to a hospital, you collect the data from the patients, and you collected it and you created a model. Okay, no problem. Now your model is giving you the accuracy of 95%. Okay, accuracy, or I should say performance measure. You are saying 95% your model is good. Okay, we can deploy it in the hospital. Now in the hospital, again it will be tested. Okay, for each month, or you can say per week, there is will be some evaluation. So in a week, the patients who have visited the hospital, they check the app. So your model is on the app, it's on the testing phase. The patients who are coming, they were be the data is given to the model and their predictions is carried forward. Now you see that for that 1 week, the new testing data, your model is acting very bad. So it means that your model has overfitted. So this is the major observation that we can find out. Getting my point?
Yes, ma'am. It's
Okay.
that during testing we will identify whether it is overfitting or
Yes,
not.
you can say that. Yes, yes.
Thank you so much, ma'am.
Okay. So now I was talking about data augmentation. Okay. So let me ask you one question. My question is, okay, I give you some the task of face identification or something related to your the human face. Okay, so whether it's a classification, recognition, or anything else. So the human face is more like, it will be more like some eyes will be there, nose will be there, some mouth portion will be there, some hair will be there. Okay, so this is like a human face that you have collected data of multiple samples. Let's say 1 million or something samples are given to you. Okay, you put that data, huge amount of data, in any good model, and you created the model in a good way, the 99% accuracy. Okay, just let me know whether your model will be giving you good results if in the test set my input is like this. So if I give the input like this is my test. Okay, so do you think your model is able to handle this?
No, ma'am.
Depends, right, ma'am?
I am saying, okay, so there are mixed things, because some of you may be like कि, today is the era of Gen AI, artificial intelligence. This is a very simple task that I have just given a face that is upside down. It's nothing like, it's not very difficult, correct? Yes or
Yes,
no?
ma'am.
Right. So let me give you one explanation for that. Uh, Look, your model. Someone said anything?
No, ma'am.
Okay. So basically, just think about this. Whenever you are training on any type of data, that data is just, you can say for a computer, it's just a mixture of some numbers. So those numbers are coming from some distribution. So if I am giving you the face in this sense, and if I am giving you the face in this sense, the data distribution will 100% different. Reason, there are two eyes here, and there will be never two eyes if I give you this upside down face. Okay, so your features that will be calculated from this phase cannot be applied from this phase until you just apply some rotation mechanism here. Okay, so basically what one good scientist say that if you are training on the faces like this, you can't test on data which with faces upside down. So it means that we have to intelligently include some faces which are upside down also. Okay, so what we can do is, so some person say, it's a very simple thing. All the training data that you are having, make it upside down and give it to your model also. So it means that, let's say we have here 100 samples plus 100 samples upside down. Why can't we do that? We will have 200 samples more data and we can process it. If the model has seen this upside down data, then it's okay, then it is able to test. So this is called augmentation. Augmentation means the same data is augmented or transformed into some another sense and passed in your model. Okay, now there are two things related to this. As I told you, कि that person say 100 is your original samples, 100 is your augmented samples, means upside down samples, I can say. Okay, so now you have 200 data points. Okay, they say okay. Another scientist comes here and say, why to include 200 200 data points, only 100 were sufficient. So what we can do, we can say, let's say one sample is coming, so with some probability I can include it as it is, or I can use its augment part. So it means that from these 100 samples, maybe some of the samples can be passed with the original image, and some of the samples can be upside down and pass into the model. This can also be happened. So these are all data augmentation strategies. So data augmentation means it is increasing the variability in your data. Okay, so generally we use rotation and some brightness change and some scaling. It means some bigger object, smaller object, we use these type of small things on the images or on the data, so that we can say that these type of data can be included at the testing time. So in our sense, what whenever when we are doing for plants actually, so let's say some drone is capturing the images from a single site, but at the testing time the farmer can click the picture from the sideways, from the top view, from the bottom view, any view it can click the picture to. So your model should be robust enough so that it can handle all these transformation. So this is also a problem of overfitting, because when I say you have collected data in very restricted form and your testing data includes some rotated image, it will not work well. So you will say your model is overfitted, right? So this problem can be handled with the help of data augmentation techniques. It's a huge study of data augmentation, whether on images, whether on videos, whether on which type of data you are having basically. So this data augmentation can be one of the measures to remove overfitting as well. So whenever we are doing any model training, especially in deep neural networks, in deep learning, first we apply this data augmentation when we capture data. Second, we apply dropout at some levels with some probability. So these are the things that we apply initially, thinking of ki we are obviously there will be some overfitting, so we will apply them without thinking ki whether it is or not. So these are some precautionary measures that we are using for removing the overfitting or for the generalization. All right, another concept is in this domain as active learning. Means just think about this, the problem of overfitting is open now. Okay, so multiple scientists are working in different fields, so they have different perceptions. So one say ki whether dropout can be worked, okay, we can include. Some say data augmentation can work, it's a different study. How the data should be augmented, what are the different strategy, it's a different now branch, but it's a one way. Another way, some scientists come and say active learning. So active learning, what they are saying, when your data is not representative, maybe you have some data of unbalanced type. Maybe you have some data, let's say you have 100 samples. Out of 100 samples, 80 samples belong to young people and 20 samples belong to old people, and you are creating some age detection model. So this data is not representative, it is not representative of the whole population, right? And because your data is 80% having young people, your model will be biased towards this side, right? So what they say that active learning says ki add some means add this sample additional data from regions with high uncertainty. So they say that if you have this type of thing, we can work towards active learning. Active learning means it's not like balanced. So let's say if your data is more like that, choose some of the samples. Let's say 180 samples are here, 20 samples are here. Choose 20 samples and 40 samples here from here, use for training. It's more like that. It means that you choose more samples from the regions which are prone to uncertainty, because if you are creating some model, obviously the model will be biased towards this side, so the errors from this side should be more penalized. It's more like that. So work towards those errors, work towards those sides which you can find that here the there is more uncertainty or there are more chances of errors. It's more like that. So ये इस तरीके की बात हो गई आपकी. Let's say in a class there are multiple students, and some students are by time, by having a session of 2 months, 3 months, a supervisor can be aware of which students are good at which task, right? So let's say I have a task and I know that some of the students are good enough, so I will not pay more attention to them, but I will pay the more attention where I can have an idea that these students can make mistakes, so I will ask them more. Are you getting my point? Are you is that clear? Is that clear? I will not ask this much these many questions to the students who are, maybe they can ask. I can say that. So I am putting more efforts toward that side which I know there are more uncertainties. So it means that it is type of active learning. Okay, so active means we are putting our active sides where we can find difficulties. So the model actively queries for more samples in the critical areas. So generally we go for the testing for the areas which are more critical, you can say. So it can also help to reduce bias in the data, because 80%, if I am saying young, so it is obviously the model is biased toward this side. So we can do like, if we are able to give more preference to the 20% side, because traditionally the model will be giving more preference to the young side. So some strategy can be put forward that can prefer the 20% side in place of 80% side. So this is called active learning. Okay, another type of mechanism come that for overfitting ki, let's say you have created a model and you give me an answer and you are just optimizing it. Okay, okay, okay. So if you are giving me some answer again and again, it is more like degrading the performance, right? So what can you do? So another concept come here as ensemble learning or weak classifiers. So weak classifiers means, let's say, firstly I have to define the classifier as a weak or a strong. So if there is a strong classifier, it means the training error is more like 99%, testing error may be like 98%. So it means it's a strong classifier. It is able to handle things at the testing end. It's okay. Weak classifiers are more like classifiers slightly better at random. Okay, so for example, if I am saying there is a accuracy of 50%, 50% means your classifier is highly random. It is not knowing anything or near to random. But if a classifier with 60% or 70%, these are also not good, but these are weak classifiers, means some of the data is not classified correctly, some of the features that should be learned is not learned. Okay, so these are the weak classifier. If we can identify these weak classifiers, we can work for that. So it's more like that. Let's say if I ask a student some question and that student is not learned well, he or she is giving me some random answers. Okay, maybe one day he get 90%, another day he get 20%. So it means, and on average it is morely looking like 50% type of thing, right? Weak students are which students, which are more like they are not actually random. At least they are not random. They are thinking of, they are not able to put means give me the correct predictions for most of the answers, you can say, but still they are getting some concepts. So maybe for some concepts they are good, for some concepts they are not good. So I have to identify. If I can identify those weak students, now I can work on them. So it's the same process here. If you can identify that this is a weak classifier, you can work on them, right? So this weak classifier we will be using in ensemble type of learning. Okay, so one of the ensemble method that can be used here for weak classifiers is boosting. So what we can do is, let's say I find out a student who is not able, who has understand the concept of the supervised unsupervised, is able to grasp somehow SVM, but it's not, he is not good at neural networks. Okay, so what I can do, I can put more efforts. What I can say, I have, I can call that student, I can say, ki, okay, you have got the concept till SVM. We will not discuss about it because you know it. We will talk about what you have not learned. Okay, so I can put efforts on the areas or on the topics uh, which is not easy for that student to understand. Here also this boosting means it combines the weak classifier to form a strong model. It means that it combines the weak classifier, it finds out where which samples that classifier is not working well, then use those misclassified samples to again train, then use those misclassified samples to again train. So it means that it is boosting the performance on the misclassified samples. That's why it is called boosting. Okay, and one of the boosting algorithm is written as here as ADA boost. It is one of the algorithm. Another type is bagging. We are going to discuss this in the last of this lecture as well. So bagging means it's more like let's say I am not able to find out any weak student from your class. Okay, and I don't know whether you have learned well or not, I'm not sure. So what I will do, I have a task. What I will do, I will divide the task in some split the task in some ratio. Let's say I have a question to check. Okay, so I have a task that I have some thousand questions to check related to machine learning. So what I will do, I'm not sure which of you are able to give me all correct answer, right? So what I will do, I will create a bunch of some, let's say 20 questions. So 20 question, and you are 50 students in the class. So what I will do, some 50 20 questions, I will create a set with 50 for 50 students repeatedly. It means that maybe some questions can be repeated for 2 students or 3 students, it doesn't matter. And I will pass all this question to you because I don't know the answer. I want to check whether you are able to give me a correct answers or not. So I will just do that. So what I can do that, let's say question number A is given to, let's say, some 5 students or 6 students. So I wanted the answer true or false. I don't know the answer. Okay, this is from the testing purpose I am saying. So from those 5 students, because I don't know which one of you is the better learner, I will take the average. I will take the majority. Okay, from those 5 students, let's say 3% say it is true, 2% say it is false. So I can take the majority. I can have that, okay, it can be true, right? Because there are high chances that if you all are average or good students, I am saying, okay, so this strategy comes into this bagging type of concept. So where what you do, you create multiple copies of data set in small amounts and apply some classifiers on that and take the average or take the maximum voting or something out of it. So this is called bagging technique. Okay, so these techniques can be used to you know uh, to elevate your systems, maybe I can say, because there are some pros and cons of every classifiers. If you have gone through with neural network, svm, decision tree, okay, these are multiple algorithms or classifier for classification. So there are some pros, there are some cons of each and every algorithm related to data. Obviously we don't know which will work for us, so it's more like why not we include all of them, right? So that's why it is called ensemble. Ensemble means mixing together, or you can say ki collecting the information of from multiple sources. So that's why this type of learning also comes into picture to reduce this overfitting thing. So let's say your decision tree is overfitted, but your neural network and svm is not. So maybe your neural network and svm can give you good answers irrespective of overfitting in decision tree. So these are the things that we can explore here. Okay, so now we will be seeing that all of this are more like these are the things that I have defined. Now let's go in detail. So first thing is, we have learned this cross validation already, and we will be using this bagging technique. So bagging means bootstrapping. So maybe let's talk about this bootstrap. So bootstrap, as I tell you, that it's a sampling technique. So I gave you an example. Let's say I have 1,000 question to make an assessment, and what I will do, you are 50 students there, so I will make a set of 20 questions 50 times. Okay, it will be like less samples, right? More samples, that there are, I am saying 1,000, right? And you are 50, so it should be 100. 100 or 80 I have created a set of 100 or 80 and I divided among you all 50. Okay, so this sampling, how I am sampling it, I am sampling it randomly. So bootstrapping is a similar way. So look here, this is the size of data set, these are all 1,000 questions I have, right? And this is the n size of 80. So with some probability I fetch some 80 questions here. With some probability again I fetch some 80 questions here. So these are repeated, this can be repeated. Okay, so it's more like bootstrap means a bag is there, just and there are multiple data sets and data points inside the bag. Just uh, um, uh, keep out you, yeah uh, uh, pick out pick out some n data points out of it. Okay, so here also this is 80, here also it is 80. So these 80 samples can be drawn from the original data set with replacement. This is called with replacement. And in cross validation, I told you, these are mutually exclusive, these are not replaced. Okay, so if some samples are there in a b c d, they will be mutually exclusive. So this is the very big difference between bootstrapping and cross validation, that whenever you are using bootstrapping, it is always with replacement, and whenever you are doing cross validation, it is without replacement. Okay, so this bootstrapping thing helps to estimate variance and classification error and you can estimate, this. For this you can apply one classifier, this you can apply second classifier, this you can apply third classifier, here you can apply fourth classifier, even you can apply same classifier as well. It's not an issue. Okay, so it's more like that, whether you are using cross validation type of thing or bootstrapping type of thing. So there are two methods now you can apply, in which you are feeling you are comfortable or more good for your data. So this is called bootstrap. So it is written as the algorithm as well. Basically there is one disadvantage of bootstrap. Why? In cross validation, let's say k fold, This is fourfold. So this is your testing, this is your testing, this is your testing, and this is your testing for four folds. In all the four folds, you are 100% sure that you have used all the data. Okay, because this data is used as training, this one is testing. In the next fold, some changes will be there, but all data will be used. You are sure that after four folds, even after single fold also, or after four folds, I can say each and every sample can be either in the training or in the testing set for once at least. Okay, but in bootstrap there is no assurance. So there is no assurance. Maybe there are in the let's say there are four bootstraps of 80 samples, I can say. So maybe here a is used, here also a used, here also a used, and here also a used, but in from the data, let's say d is not used here, here, and here. I can say that it can be possible कि d is not used at all in the bootstrapping thing. Okay, so they say that it should be given some percentage of probability that how much data is certainly going to be used. So the method is called this 0.632. So it means that they are saying on average 63.2% of the data appears in any given bootstrap sample. It means if you are trying for a bootstrap technique, we cannot assure that all the data samples will be used, but we can say that on average 63% of the data will be used. So the remaining 36% is left out. So it will never be used in any of the bootstrap method. Means this is a possibility on average. Okay, how they have created it? So what we can do is the data that is used in bootstrap and data that is not used in bootstrap, we can apply two algorithms here and here and take some weightage strategy. So basically this is your bootstrap data, and this is the data which is not coming into bootstrap. You can find it out and apply some techniques to remove this 0.62 type of thing. Yes, any doubt?
Ma'am, is there any way to identify that data's, I mean, like those were not sampled?
Yeah, it's very easy. Just think about it. You have 100 samples, okay? Correct? You have
Yes,
100
ma'am.
you have
Okay.
100 samples, mean give some ID to each sample. And when you sample out in first bootstrap, let's say you sample out some 80 samples here. Okay, 20 will be remaining.
Okay.
Okay, so let's say those 20, you know these 20. Find out these 20 in another bootstraps. If they are found, then okay. If they are not found, then it is left. It's more like a searching algorithm type of thing.
Ma'am, from my understanding that generally this is the probability in case of bootstrap that only 63% of data is used. That is what is this concept, right, ma'am?
Yes, it's only a probability. Yes. I'm not saying
Yes.
it will be 100% valid for every case. No.
Yeah, I understand. Even sir said the same, ma'am.
Hmm.
Uh, but sir never mentioned about handling the left out data. So I'm just curious, like
Okay.
any
Okay. So
like
look,
actual method is there.
what we do is na, we have applied bootstrap. Okay. We don't know. You don't have to go this by the traditional means ki if you are starting, you have to do it. No. Let's say the bootstrap technique is not giving you good answers. What you will do?
We have to change algorithm, I
Right,
thought.
right. So you have to think of the ways where the problem lies, correct? So
Yeah.
the one problem can be because of this. Maybe some data is not included here. So let's find out which data is not included here. Getting my point? Just think
Okay,
about
ma'am.
this. If the condition is, because we are not training you to follow some steps which are very crisp. We are telling you the steps that these can be are possible ways. If you find a difficulty, what you can go up, what you can check towards that this might lead a problem, this might lead a problem. because problem is not fixed. You don't know anything about, because it is completely random. Either reiterate the process, you can say that, but you just think about it. About 36% of data, 36% of the data is not used on average. So let's say this is a true value. Okay, so it means that 36% of the data can be used for testing also. If you know that any of these bootstrap method don't have used this type of data, we can use it for testing. We can evaluate on that data as well. That can give you a good performance measure as well. So we can think in this direction. It's more like that.
Ma'am, I understand those things, ma'am. Like, I'm just curious that is there any method to identify this 36%? I mean, any method like we call
No,
it a booster.
how we are saying, means, are you asking me that how mathematically we are saying only 63 is the
No, no, no. That I understand. That I understand 63 and 36 and all.
hmm.
What I'm asking is there any procedural call to identify the 36% which is not sampled
Yes,
during
it's
this bootstrapping
yeah,
process?
yes, you can na. It's a simple process na. Look, as I give you an example, let's say you have bootstrap in a four steps. One, two, three, four. Okay. So at first bootstrap, let's say 20% of the data is left. I'm not saying 36, I'm saying 20%. Okay. So from the 100 samples, 20% left out. All right. Okay.
Yes, ma'am.
When you apply bootstrap for the second process, from these 20%, find out how many are there in this second bootstrap. So let's say there are 5% here. So remaining is 15% left. You can
Okay,
simply
ma'am.
check it out now, sample by sample. You have some idea or something ki whether it is in this sample or not. It's a simple, it's more like that ki you have a dictionary and you have to just, in Python you have to check whether this term is in dictionary or not. So it will give you true or false.
Ma'am, I understand the process you are telling, ma'am. I don't have any problem with that. I'm just asking any method it is doing this so that
No,
I
no,
can
no, no,
refer
no,
that
no,
method
no,
for
no,
you.
no, no, no. It's not any method. Presently, I'm not
Oh,
doing. Huh.
okay, 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 ma'am. Thank you.
Okay, so this is how, this is the probabilistic measure. You can go towards it, that how this magic number 0.362 is here. And this is we have already done. So basically I can compare the bootstrap and cross validation on some features. First is sampling, which I already explicitly mentioned, that bootstrap it with replacement, cross validation is without replacement. Data size, bootstrap we need a large data size, and for cross validation it can work for a small data set as well. Why? Because in cross validation you divide the data into some parts, into k parts, and k minus 1 parts are used for training, so it is good. But in bootstrap you need a large data set, so you can sample a subset out of it. So if you are saying ki I am taking 100 total size and I am taking out 80, then it does not, means it does not make sense to use bootstrap here. Bootstrap can be used as more like, if you have some uh, means thousand, 10,000 of the data, and you are taking some 80% or 90% of the data, or you can say 70 or 80% of the data, then you can go for the bootstrap. Variance reduction, then you can say that both the steps go for variance reduction, because some of the data will be, reusing every time. Use cases is where bootstrap can be used. Bootstrap can be used for variance estimation and error estimation, obviously. And for cross validation, it is used for model evaluation and hyperparameter tuning. So generally we use cross validation more often rather than bootstrap, because for bootstrap we are just going to use for error estimation, how the error is going to be calculated on different bootstrap areas. Okay. Next thing is this leave one out cross validation is basically a type of cross validation. It is mentioned in your videos as well, so that's why I have put it here. Here leave one out cross validation, here it's just that the testing size is always one. or you can say that the number of folds is equal to the number of samples in the data set. So it's more like it is using all the data for training, just keeping one testing sample, but it is very computationally expensive, so we don't use it. Okay, so it can be helpful for that thing to make out the observation that which sample is most critical. So it's more like that if you have all the data except one sample in the training, and you are testing on this single sample and it is not giving you good results, it means that this sample is somehow very different from the training data. So this can be helpful to find out which are the challenging samples in your data set. There are multiple other ways also, but using cross validation you can find out this thing. So it's written in your course, that's why it is also present in the PPT as well. So leave one out means here the k is equal to n and testing size is simple 1. Any doubt?
K equal to n minus 1, right?
K is equal to n. N, k means number of folds. So number of folds will be n, and you always train on k minus 1 set. So that's why it is written train on n minus 1.
Okay, ma'am.
All right, so some challenge and best practices are written for bootstrap and cross validation. So I think this all we have covered, so I will not go in this. Okay, this is a very important topic of confusion metrics. So basically, we have seen some evaluation measures related to classification. The very common is accuracy, but accuracy is not very good measures when your data is somehow unbalanced. For example, let's say I have a data in this form, class A and class B, and your model is learning class A very well but not class B. It means that the model, let's say, has some accuracy of 80%. It means all the samples here are correctly classified, but this is not correctly classified. Okay, so when you see the final performance as 80%, you will say your model is good. But if I go in the deeper analysis, I will find out that it is able to only predict class A. It is not going to predict class B. So it means that your model is not good for class B. And if it is not good for some class, then obviously your model is not good. So that's why we can say that accuracy single is not a good parameter for performance. So here comes another parameter in which they create a matrix of multiple parameters. So this matrix is called confusion matrix. So this matrix gives you the summary of prediction versus actual values. So how many actual values are there, how many predicted values are there, we can get it from this matrix. So basically, one of the rows or columns can be interchanged first thing. So you have to make sure whenever you are reading this confusion matrix, what is written where. So here it is written these are actual and these are predicted, and these are actual. So it means that this column is saying that if the actual value is positive and the predicted value of positive, let's say here it is written as 40. So 40 samples which are positive are predicted positive. It means like that. Okay, similarly here if it is written as 20, it means negative samples are predicted as positives are 20 samples from the data set. Okay, so here let's say it is written as 10, 20, 4, 5, 6, 7, 8, 9, 10. It is 30. So 10 samples which were positive as predicted as negative, and here negative samples are predicted as negative. So it's more like this table is very much clear to you. Okay, so generally you people get confused because directly the question can come like, let's say there are mm, uh, let's say in a hospital there are some total there are 100 patients, out of them 80% have disease, have fever, and from a model, okay, so let's say some 20 persons are detected with fever, or in some sense some question is given to you, some in some scenario. At the end they ask you that what is the true negative of this model. Okay, so generally you got confused ki what is written, it is true negative, is it false negative. So let me give you one what I can say is that it's easy to go to remember this. I generally do that. So you can find it out. There are two values here for these matrices. First value is either true or false. Second value is either positive or negative. Okay, first of all, start with the right hand side value. So this value is for predicted. So if it is written as positive, it means it is predicted positive. Okay, so you can say here it is positive, here it is positive, it means it is predicted positive. So first of all, go for this value. If someone asks you what are the false positives, it means that positive means it is predicted as positive, predicted as 1. First thing. Second thing, you have to check whether it is true or false. So true means same, false means different in actual. So it means that false positive may, first thing, the it is predicted as positive, but it is written as false means it is predicted positive in predicted, okay, but not as positive in the actual sense. So it means that predicted it is positive, actual it is negative. So you can find out it out ki here it can be find out this is false positives. Is that clear? Because sometimes either confusion matrix is given to you, they directly ask you what is the false negative, and they interchange this actual and predicted rows and columns. Every time generally people get confused. So I generally remember like this. First start with the right hand side, whether it is positive or negative, it is for predicted value. Then the left hand side, if it is true means same, false means different in the actual value. So this is how you can simply write out that what are the true positives or false positives, or whichever values they demand in the questions. Is that clear? Any doubt here?
Ma'am,
Ma'am,
is
is
there
there
any
any
difference
difference
between
between
precision
precision
matrix
matrix
and
and
confusion
confusion
matrix?
matrix? What is precision matrix?
Actually,
Actually,
there
there
are
are
some
some
parameters
parameters
I
I
read
read
from
from
some
some
book,
book,
so
so
I
I
just
just
want to
want to
know,
know,
ma'am.
ma'am. No, means I don't know what is precision matrix. If you can give me an idea, then I can let you know. I never heard of precision as a matrix. Precision is a completely different thing. This confusion here, it is written as matrix, and precision is a matrix. There is a difference.
Okay, okay.
Okay. So these are the values that makes a confusion matrix. Okay, so here, from here you can get that how many which classes are more important, how many values from which classes are correctly classified, how many values of which classes are incorrectly classified, so you can have an overall idea. Okay, so from this we can define some another parameters. First is accuracy, which we have discussed in the last class, that accuracy is the summation of this main principal diagonal, true positive and true negative, divided by the total number of samples. Okay, so it's a simple thing that how many samples are correctly classified. So it's more like the addition of the principal diagonals divided by the total number of samples. It's simple. It's not that difficult. Another thing is precision. So precision means true positive divided by true positive plus false positive. अब क्वेश्चन ये है, आपको एक मैट्रिक्स दे दी है, and here 4 values are written, here it is written these are actual, these are predicted. Okay, and they will ask you what is the precision. So the formula is simply TP by TP plus FP. This you know, but you get confused whether is it TP, is it FP, or is it FP. You always get confused. So now make sure before going to the examination, please make sure ki you are getting the correct values of these four parameters from this confusion matrix correct. Okay, so precision is from this area. Precision means on the user side. So if I tell you about precision from the user's point of view, so think about it. When you search on the Google, the search engine gives you around 10 to 15 responses on first page. Okay, so let's say you search about these deep learning networks and it gives you some 10 suggestions. All right, so from those 10 suggestions, let's say 8 suggestions are good. So from your perspective, you got 10 suggestions, out of them 8 were good. You say the Google is 80% correct. So this is not your accuracy, this is the precision. So what you are seeing at this end after making the query, from that you are finding out how much it is correct. So this is more like from the positive values which are shown. Okay, these are the positive values from the model. So these positive values, out of these positive value, how much it is correct. This is called precisions. Okay, so it measures the correctness of positive predictions. All right, and it means higher the precision, fewer the false positives. It means, let's say ki on the first page all the 10 or 15 samples are of your related to your query, you will say Google is 100% accurate. So you should not say accurate, you could say Google is 100% precise, because on the screen whatever it's shown to you, it is completely related to your query. So on the screen means on the positive point of view, predicted positive, how much it is correct. So this is called precision. All right, now second question is, this is from the user side, that's why I say let's think about developer side. So from the developer side, let's say you are talking about deep neural networks and there are 100 pages, or let's say there are 200 pages related to deep neural networks. Okay, out of those 200 pages, the search engine gave you 8. This is called recall. So it means that the system is able to recall only 8 samples out of 200 samples. That's why this recall or sensitivity is important from developer point of view. Okay, I'm not saying that it should be 100% or 1, but if you are demanding 10 pages, it should be 10 by 200. It should not be 8 by 200. So from the developer point of view, recall is important. So recall measures the actual positives are correctly identified. So it means that it is from actual process. From the actual values, how many are classified correctly. Okay, so recall and precisions, because it is from different point of views, we can't say that one is an important measure. It depends on the application. For example, if I talk about medical applications, then obviously recall is much more important, right? Be- uh, because we don't want a system to misdiagnose any disease that is being suffered by the patient. Okay, so let's say ki I have a disease of malaria, I went to this system and they say no, you are perfectly fine, I will not able to get cure of it. So that's why recall is a very important measures whenever there are medical type of applications. All right, so one of the scientists say ki if both are from the different perspectives and accuracy is obviously is not a good measure, then what we can do, then they say that this trade off, because this precision and recall trade off is generally seen, because somehow in some cases precision is high and recall is high or precision is low. So they say take a mean out of it. So we can simply take the mean like precision plus recall divide by 2. This is called average mean. Or I can say it is not, it is arithmetic mean. Okay, they are not using this. So they say, let's not take arithmetic. Let's say we are taking harmonic mean of precision and recall. So what they are doing, they are taking the harmonic mean of precision and recall, and the term is called as F1 score. So it's more like it's a mixture of these precision and recall. If some application is not dependent on a particular type, then we go for this F1 score. The formula of F1 score is 2 into precision into recall divided by precision plus recall. It's more like that, n upon 1 by f plus 1 by p, if I'm not wrong. It's the harmonic mean formula is like that. Okay, so it is generally used for imbalanced data sets, or if for any classification method you are using, we generally report F1 score. We do not report this accuracy or these type of thing. Sometimes F1 score and accuracy are similar, so it means that your system is good. Okay, so this is what we have already discussed. This is already discussed. This is more like, okay, so this recall thing, or now we have gone through with multiple type of accuracy or these performance matrices for classification. One type of concept comes into mind when there are discriminative analysis. Okay, so let's say, which I asked you also, that let's say we have some data here and we have some data here, and I create this decision boundary using SVM. From this decision boundary, you are able to correctly classify this sample and this sample, so it means that accuracy is equal to 1. Okay, now one scientist say that because you are working towards testing, let's say they say, if this boundary is shifted somehow left and right, what will be the effect on testing? So they say that let's find out that if my boundary is shifted towards somehow left or somehow right, then what is the effect on my testing? Why they are using this observation? Because if you can understand like that, any system that comes to market, they comes with proper manual and everything, right? So they give analysis report related to the mishappenings with the system. Let's say they are saying ki if some electrical appliance need like 200 voltage, so they write there ki if somehow plus minus 5 voltage can be tackled by the system, but if more than this percentage of voltage is plus and minus, then obviously the system will not work. So how they are going to do that? From these type of analysis, let's move the system here and there and find out what is the changes in the testing or performance. So in the similar way, they what they did is they created this boundary, which is a perfect boundary. Okay, then they make it somehow shift to the left, they make it somehow shift to the right, and they say how much accuracy is there. Okay, so if that accuracy drops too much, it means a single variation in your samples, in your model, is creating large effect on your testing data. It means somehow there are some overfitting issues. Obviously your model is not generalized. Okay, and if making some changes is somehow affecting the system but not much, then we can say that okay, these much variations can be acceptable. So these are the techniques that you can apply to analyze your data, because this branch, okay, this machine learning is a important tool for ultimately data analysis, and analysis has no boundaries. You means you are getting out some values from the system, and now how to analyze, how to put conclusions with the values, it dependent on the developer, that how you see them, what you conclude them, right? So here also generally we use some errors like top k values. If you have, some of you have gone through like top 1 accuracy, top 2 accuracy. Top 1 means, let's say, uh, 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 for example, if I give you an example, let's say I have to predict the number of students in the class. Okay, so the fine and multiple photographs of the class are given to the model. So accuracy is, if the number of counts are correct, then it will give you 1, otherwise 0. If I say, if I have a tolerance of 1 or 2 student count, it can happen, right? So how much tolerance you are allowing in your system is called top k or tolerance k type of thing. So this is the similar way. So what can happen if some shifting -1 -2 +1 +2. So this is how you are analyzing your data as well. So for that there are two things, that is true positive rate and false positive rate ultimately. So the formulas are written here, you can simply find out these things. So we have learned from first of all, these four values are so much important, these true positive, false negative and true negative. You can calculate accuracy, you can calculate precision, you can calculate recall, you can calculate F1 score, you can calculate true positive rate, you can calculate false positive rate. It means these values can be asked in any form, and it's very simple to calculate. It's more like the plus and division rule, that's it. But these are quite generally you people are confused in that. And this question which can be can be correctly done in the examination, generally you people stuck here just because of some confusion. So make sure that the formulas that you remember is correct, and these values are placed on the right cell. Okay, so these values, true positive rate or false positive rate, are used to plot a curve that is called ROC curve. Okay, so let's talk about this ROC curve. So ROC curve, the full form of ROC is receiver operating characteristic. So it has two axes, obviously it's a graph. So the x-axis and the y-axis. On x-axis it is false positive rate, and on y-axis it is true positive rate. Okay, so true positive rate is sensitivity, this, and it is called as recall also. And this is called specificity. Sorry, this not this, but 1 minus FPR is called as specificity. So basically we plot these curves, we call that curve as ROC curve, and we see this figure like structure. Okay, so when you plot this false positive rate, true positive rate here, okay, here, so you can either get this line or this line, or any graph like this can be, this can be. So basically this shows that how much accurate is your model is. Okay, how you calculate it, let me give you one example. So first let me give you one example how to calculate this. So this ROC curve is a better approximator, a performance matrix, where these tolerance which I was talking about can be handled, can be visualized. How? So see here, this is your true label, okay, actual label, and this is your predicted. And these are the probabilities. I told you that there is a softmax function applied at the last of the neural network which gives you the probability. Okay, so on this probability we find out that the class is this much accurate. Okay, so this is your given data, this is your initial data. What I will do is, because I was talking about tolerance, so tolerance means on the basis of probability. So first of all I sort this table on the basis of this probability. Okay, so let's, because for the ROC curve you have to calculate TPR and FPR. So for that TPR, FPR, you have those formulas, and for that you have to calculate true positive, false positive. It's more like that. But how to calculate it? Let's see here. So what you will see, this is your sorted table. This one. This is your original table, and this is your sorted table on the basis of probabilities. Now you put threshold. So how you put threshold? You first put threshold on 95, 992, then 90. If you are putting threshold on 95, it means all the samples below 95% of probability will be treated as 0. It means that you are choosing a system where only 95% probability is giving you 1, otherwise no. So in another sense, if I say, if I am choosing a probability of 95% and my true positive rate, or these rates are about 0.98, it means with so much probability your system is correct. It's more like that. So generally we want to find out how much tolerance is there in your system. So if if it is able to handle the classes with so much accuracy of 95% probability, then your system is so good. It's more like that. As you decrease the probability, obviously the accuracy will be higher, because if you are saying if I keep the threshold at 0.30, it means before that all are 1, after that it will be 0. So it means that more chances of you know it can happen that, because means both things can be happen. Let's say ki 0.30 se upar if you are taking it as positive and many of the samples are negative, it means something is mishappening, right? So that's why they are putting thresholds. So let's say the threshold is given like this. So this is your table, this is your table, and here the threshold is. So see, if the threshold is 1, what is the true positive? True positive means if it is already positive and predicted as positive. So for 1 there are no true positive, because the first probability is 0.95. So here it is 0. Okay, for 0.95 probability only one sample is correctly classified, true label. Okay, so it is only one. For 0.92, there are two samples. For 90, look, till 85, there are these many samples. 1, 2, 3, 4, 5. These many samples are true labeled and true predicted. For 0.70, just think about this. Here, it is also be predicted as 1, which is not correct. I am not saying about correct or not. I am just saying keep a threshold on the probability and find out how many are correct, how many are not. So using this table, do one thing, go to your home, use this table, put the threshold like this, and calculate all four things: TP, FN, FP, and FN. If you can calculate all these four values, you can calculate true positive rate and false positive rate easily, because the formula is given to you. Let me explain it again. The table is given to you with true label and predicted probability. Predicted probability means these are the probability of getting output 1. Okay, so I put the threshold at each and every probability. If I am putting a threshold of 0.70, it means 0.70 and higher probability will be counted as 1, rest will be counted as 0. And using this description, calculate the confusion matrix, and using that confusion matrix, calculate TPR and FPR. So whenever you are going to get the values of TPR and FPR, just look here. First value is 0 0, second value is 0.110, third value is 0.2220. So it means that these values will be helpful for creating the graph that I told you, ROC curve. Using this graph, if the graph is having a perfect shape like this, if this is the graph and you are getting the perfect shape like this, it means you are getting a good model. If this is somehow low, then the model degrade. And if it is only this line, this diagonal line, it means the model is completely random. Completely random, because this line shows complete random points. That's it, 50% accuracy. Okay, so this is called ROC. And if you calculate the area under this curve, then it is called AUC, area under curve. So this matrix is very important. Somehow generally that whenever there is a classification system, generally people plot this and say that look, these are the tolerance limit, and with these recall values I am getting a good curve. So it means that there is a so much high probability of my system, it is giving better answers. Okay, so this is a ROC curve thing. Any doubt in ROC, please go ahead. Is it clear, ROC curve?
Yes, ma'am. Can you explain FN for 70th true label predicted probability value?
What what did you ask?
Ma'am, I want to know how to calculate FN for the predicted probability of 0.70.
For this probability, what you are asking about F1 score?
Fn false.
Acha, Fn. Fn.
Yes.
Okay, what are false negative? False negative means predicted negative, but it was actually true. It means predicted 0 and actual it was 1. Correct?
Yes, ma'am.
Okay, you are asking about 0.70. Correct? This is 0.70.
Yes.
Okay, so for 0.70, 1, 2, 3, 4, 5, 6. एक minute. So six values are predicted as 1. तो prediction में आपकी 6 values 1 है. Okay, and there are true labels are 1, 2, 3, 4, 5. So 5 out of 6 values are correctly. So TP is 5. It is correct. Okay, this is correct. Now I have to,
Yes, ma'am.
yeah, I have to take out predicted 0. How many are 0? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. These are zeros, but actual how many are 1? So from here I can get 1, 2, 3, 4. 4. See again. See again. I want to calculate Fn. Fn means where predicted is equal to 0. Find out which are predicted 0. So this is your Fn means 0.70. Less than 0.70 are all zeros. Okay. So these are predicted zeros. Correct. Out of these, which are actually 1? So which are actually 1? 1, 2, 3, 4. So 4 will be the Fn value.
So that would be the wrong ones, right? Whatever is
Okay, ma'am.
one but actually less than. Where did you choose point 0.7 from? I'm sorry if I may have said that.
0.70 where I have chosen.
Yeah, like how did you choose that threshold? Like, is it already uh,
No, it is not
predetermined
defined.
or?
It is not defined. Generally, what we do is when you plot these graphs, you give some threshold according to your comfortability. You start with 1, let's say 0.95, 0.90 till 0.70 in a regular interval.
Actually,
Okay.
actually, ma'am have calculated the threshold. I mean, with all the values as threshold, someone asked zero point 0.7 as threshold. How to calculate?
Hmm. If you are asking me how to choose threshold, then there is no perfect way. We generally go start with 1 and go down. If you are going down till 50%, then it does not make sense, right? So if you are saying ki 50% you are choosing as a threshold, then it does not make sense for your system. So at least you can, means at the max you can go till 70-30. That can give you a good result. You can go lane down. It's okay, no problem for that. But you have to start with 1, go down. Either we generally keep it as either 0.95 9085 with 0.05 difference, or with 0.1 difference, we can say 1 0.90 0.80 0.60. We can go like that also. So it's more like you have to have this graph value. So for that you need as many as points you can choose. It's not like that. You can choose in between also. If you want to choose here 0.93, you can go for 0.93. Here, for the sake of displaying you, I have chosen each and every value as a threshold which is in this column. Just for the sake you can see that okay, what is the effect if I choose this, if I choose this, or if I choose this. Okay, getting my point?
Got it. Okay.
Okay. So this is more like your ROC curve, and the area under the curve is, it's generally more like is the representation of a single quantity, because this curve is more like in this form. So you can't be to quantify this, we introduce a term, this area under curve. So the area under this curve, the more the area will be, is called the best classifier, you can say. So if your area is more like this is called area under curve is equal to 1. So you can make out some observations from this graph as listed here. So it's more like, it's a very simple thing. You can, like for example, here the area under curve is 0.818. You don't have to do this. There are libraries which can calculate the area, and if you want to go into deeper details, it's simply the integration process. You can go and see what the integration process does here. So it takes these stripes and integrate over this line to this line. It's more like that. Okay, so it's like, if you have area under curve is equal to 1, it's a perfect classifier. If area is equal to 0.5, it's completely random, and in between the variations are quite smooth. Okay, so these are the same things which you can go. This is not very important. uh, this is not very these are the other things that you can go in a theory. It's not like that it's very important. Yes, important is this bagging thing. I told you obviously before that also, that there are two things that we have seen in ensemble technique. Ensemble ones. So ensemble में the first technique is bagging, that is bootstrap aggregating. So here what we are saying, we are training multiple classifiers. It can be of same type on different bootstrap samples. So you are dividing the big data into multiple bootstraps, apply different classifiers or same classifiers, take an average or take maximum voting or something like that. Okay, so it's more like that. The main algorithm of bagging is random forest. So we also discussed this in the last lecture, that what they do is they take a bootstraps from the data points, apply decision trees, create small trees, and take a final output as the majority voting or averaging from all those small trees. So because all trees are used up at the end, that's why it is called random forest. Okay, so this is more like a bagging technique. You can apply with any other algorithm as well. So this is first thing, that is bagging. Okay, so it is displayed with a small diagram. This is original data. You have divided data into different splits, apply the classifier, and this is the ensemble classifier. So this is ensembling, means either aggregating or taking the voting, maximum voting. Okay, so this is a simple bagging technique. Now question arises, that is this aggregating or voting is a good technique? Are these the only ones that we can use? So that's how comes into picture this stacking. So instead of giving equal weights to the prediction, we can use a meta learner. Meta learner means, let's say we have three classifiers, this and this. Okay, so let's move towards in a scenario where I have four students out of your class, and I have a surety for some student that this student is much more accurate than the other three. So I will bias towards the output given by that student. Okay, so this is a common thing that is present in the human, because let's say ki if you want to talk about some data, you want to talk about your placements, and you have a senior who has placed in a Google. So your thinking is biased towards that person, because you wanted to place in Google and someone is there. So his experiences or his suggestions are more weightage in your mind, keeps more weightage in your mind rather than the other person's. Similar here also, can we do this different weighting thing in this aggregation at the time of aggregation? Yes, we can do it, and we call it as stacking. And because some different weights are given to it, here different weight, here different weight, here different weight, it means train a classifier again. So it means that is called a meta learner. So we can choose a meta learner like logistic regression or other neural network. What it helps here, these models The weights of these models can be calculated using this meta learner over the final output. So now here simple methods aggregation or majority voting can be omitted and stacking can be applied. Why stacking? Because this is the first layer where different models are there, and this is the second layer where meta learner is there. So it means that this meta learner is stacked over this bagging thing, right? So that's why it is called stacking. So it's another method of ensemble technique. Third is your means this is all in the theory, you can read it out. Third is the boosting. So I already told you about boosting in the last in some previous slides. We can have an idea like this is the original data and some classifier is applied. Now we find out which are the misclassified points. So using this misclassified points, we take these misclassified points in the next step and apply the same classifier. Okay, now maybe some improvement has been done and another misclassified samples are calculated, and similarly we do it in a sequential step. This is called boosting. Okay, for boosting at the end we use the full sequence, not only single classifier. So what we will do, if some testing data is applied, we go towards this, we calculate something, then pass this here in this network, we calculate some output, we calculate some output from where and aggregate it. Because why? From the first step it is calculating yes or no. Let's say the classifier is 0 or 1 and 0. Okay, so these are the misclassified samples. The error in this misclassified samples is calculated in the next step. The error in these misclassified samples is calculated in the next step. So ultimately, if you are getting some output from this first step, calculate the same output from the second step, from the third step, and add them, because they are calculating errors and this is the predicted value. So in the predicted value some error is there, some error is there. After calculating the error and adding that error into the predicted value can give you the final prediction. So this is how boosting works. In bagging there it's more like majority voting or something, but in boosting you are calculating the errors at each step. So boosting is more like a sequential process and bagging is more like a parallel process. This is the major difference between boosting and bagging. So if you have multiple classifiers, go for bagging. If you have more computation power, go for boosting. You can go for boosting for that. Okay, so the algorithm like random forest we choose in bagging, ada boost is the function that we choose in boosting. Okay, I think it's not in your I don't remember that whether it is in the detail or not. So there are multiple pros and cons. So here the pros and cons are written, and for you can see here that for bagging it helps to reduce variance because multiple bootstraps are created, right? So variance is reduced, some variability is stuck, but it needs much diverse data for the base learners, because if you are creating bootstraps you need some small amount of data from a huge bag, right? So you need diverse type of learners as well. Secondly, for boosting, the process it reduces biases and it improves accuracy. Why? Because these errors are because of some biasness maybe. So from the first step, it is giving you the output and it tries to calculate the error at each steps. So it is trying to reduce the bias, how much the errors are there. But it is more prone to overfitting, because in order to reduce the errors, maybe these sequential steps can lead to overfitting for each and every samples. Okay, so boosting is not used for the system where the system is already for overfitting. That's why in literature it is given that boosting is some technique, but at present we are not using it at much frequency. Okay, last is stacking. So it is using multiple models in bagging technique as well, or we can say with or without bagging it's okay, but it is computationally expensive, because let's say you have k algorithms for this stacking. So you need to learn a one meta algorithm over the top of those k. Now it's your choice that whether you want to train with this meta learner, you want to freeze the k algorithms, don't want to train them, or only train the meta learner. It depends. So there are multiple variation of stacking as well. So stacking can be computationally expensive, but if you have good gpus or so, you can go for that. It is more like a more generalized process for different types of ensemble techniques. So this is what in today's lecture, that we have started with some evaluation criteria. We have gone with some evaluation parameters or matrices, especially for classification, but because in regression the metrics are simple, mean square error or absolute error type of thing. So we have gone through with confusion matrices or so. We understand the concept of cross validation today. Then especially the concept of this ensemble technique, including bagging, boosting and stacking. So this comprises of today's lecture. This is quite a type of lecture which is on projecting the light towards the end of your system, okay, the end of your training. So after training or post training, what can be the issues, how to look towards the results, what can be the analysis of the data, that it's more like into that projection, into that dimension. But from the next week maybe there are we will be starting, I think, unsupervised or bayesian learning, I don't remember. So this is more like a light type of lecture. Okay, so some questions are given here. Questions are quite simple, it's not very difficult. It is majorly related either with confusion metrics or accuracies, so I think you will be able to solve those. Or otherwise the questions generally are related to whether which of the sentences are correct or not, so you can go towards that. And if any doubt or problem is there, you can email me anytime. Okay, now if you have any doubt, then go ahead. Okay,
Ma'am, which model does ChatGPT follows?
which model does?
ChatGPT follows.
ChatGPT follows GPT model, generative progressive training, which is using some transformer mechanism. Basically, it is deep learning based, neural network based.
Okay.
एंड एक आप लोगों से एक रिक्वेस्ट है. Generally when I am on the pdf, I'm not able to see your messages. Okay, so if something that is required, either if you are writing in the message as well, at least switch on your mic and let me know that ma'am, I have written a query in the message. Okay, so it is, ma'am, it is used for classification confusion matrix. Is it necessary to introduce a confusion matrix for image segmentation model? So Binu, you have written image segmentation. Image segmentation, it's more like you are classifying each and every pixel under a category, correct? So yes, you can identify you can write a confusion matrix. It's just that we never give this confusion matrix officially as results, because it's for your understanding that how many pixels are correctly classified. Or generally we have another matrix for segmentation model, that is intersection over union, that how much area is correctly sampled, because we are not here for each pixel wise classification, we are more concerned about area wise classification. So that's why iou matrices are there, which are more beneficial than this confusion matrix calculation. Okay, all right, if there are any more doubts, then please go ahead.
Ma'am, actually, I have one question about the week six number six question.
Okay, what is related to?
It is which of the following statement about the imputation in the data processing in the most accurate? Okay. So the actual answer is the last one. Multiple imputation typically produces less biased estimate than the single imputation methods. But with the class, I think we got to know it produces the less variances.
Let me open the question. Then let me understand it better.
week 6.
Okay. Which of the following statement about imputation in data pre-processing is more accurate? What do you mean by imputation? Just let me know first.
Imputation means we are, it is a decision tree, right? We are uh, like uh, cutting the internal loads and
No, no. Imputation is does not mean pruning. Imputation means, let's say you have some values. Let's say you have a data of a student or of an organization. Okay, so you ask the employees about their salary. Some people are comfortable in sharing this detail, and some people are not. So maybe some of the blank spaces will be there. Okay,
yes, yes, correct.
so
Sorry, missing values, correct.
right, right. So those missing values can be treated using imputation. It means that without finding the real answer from the users, you find some strategical ways or statistical ways to impute,
Correct.
to fill that missing value. Okay. The very first imputation is remove all the missing values. Second is take the average, the
Correct.
common thing. Okay, so they are saying which of the following statement about imputation in data pre-processing is more accurate. So first statement is mean imputation is always the best method for handling missing numerical data. No, it is not, because sometimes mean is more prone to outliers. So if some outlier is there, maybe let's say the all other employees had filled the salary like 50K, 50,000, and one employee, because of some error, has written 5 crore, some extra addition of zeros. So all your mean will be shifted towards 5 crores, which is very inaccurate. So mean is not the always the best method. First. Second, imputation should always be performed after splitting the data into training and testing set. No, it should not be. Why? Because if you are after training and testing, if you are applying the imputation, it means that you are giving two different knowledge in two different splits, right? So let's say if I split the data of the organization and splitting in testing set, most of the workers are of manager category, and most of the workers are of different category in the training set, then it should not be the imputation should be irrespective of these categories, right? So that's why it should not be performed after splitting, it should be performed before splitting. Third, missing data is best handled by removing all rows with any missing values. This is not
This
a
is
good option, right? Last,
mm,
multiple imputation typically produce less biased estimates than single imputation method. So what we apply is we can have multiple category of imputation. For example, let's say I can apply first a category. Let's say I have divided the if there is salary is missing, first I divide it into different categories of your designation. Let's say manager, the clerk, the receptionist, because these type of categories will help me find the true value of that imputation can be easier. So first I divide this. Second, let's say in a manager type of thing, maybe some different imputation can be applied. In clerk type of thing, maybe different imputation can be applied on the basis of some prior knowledge. So if you are applying these multiple imputations, it will not produce any bias. If you are using single imputation like mean, it will produce some bias towards a value. So that's why the fourth answer is correct. Getting my point?
okay, got it.
Okay, all right. Any other questions? All right then. If there are no questions, imputation data precisely is to fill correct. Correct. One doubt about the circular object segmentation, is the augmentation beneficial? Uh, about the circular object segmentation. I don't understand this question actually. Circular object segmentation means you are saying there is a circle and the circle is of one class, outside the circle there is another class. If you are asking about that, is the augmentation beneficial? No, there is. I don't think that, augmentation you can generally applied on simple images which you are using. By default it is applying. If you are using any data loader, good data loader na, it will be using some of the augmentation of rotation, of brightness, or like that. Okay, it does not matter whether the object is of circular or square in shape. It is not related to that. Augmentation is always beneficial, you should apply. It's more like that. Okay, because you don't know whether when you are going to segment this, apply the segmentation on some another area, how the images will be looking like, what is the brightness, what will be the scale. So some scaling, some brightness related, some rotation related, some sharing related, so these transformation you should apply it. So augmentation should be there. Any other doubts? Okay, okay, all right then. It's good to go, so you can share your feedback here, and we will be meeting next week same time here with new contents, maybe most probably a new topic, irrespective of this supervise and supervise. If I am not wrong, I am not remembering what is in the next topic. Okay, okay, all right, thank you so much. Bye bye.
Thank you, ma'am.